Section: Introduction. In this section, we discuss the challenges of academic paper search, which is essential for research but often difficult due to the need for specialized knowledge and the ability to handle detailed queries. For example, a complex query might ask for studies on non-stationary reinforcement learning using specific algorithms. While tools like Google Scholar work well for general searches, they struggle with these intricate requests, leading researchers to spend a lot of time on literature reviews. Recent advancements in large language models, LLMs, have prompted studies aimed at improving information retrieval by refining search queries. However, academic search involves more than just retrieving papers. Researchers also read and check citations to ensure thorough literature surveys. We introduce PaSa, a new paper search agent that simulates human behavior for more effective academic searches. PaSa consists of two LLM agents, the crawler and the selector. The crawler autonomously gathers relevant papers using search tools and citations, building a queue of papers to process. It explores citation networks to find more relevant studies. The selector then reads these papers to see if they meet the user's needs. To optimize PaSa, we use the Agile Framework for Reinforcement Learning, RL. We create a high-quality dataset called Auto-Scholar Query, which includes detailed scholar queries and their relevant papers from recent conferences. This dataset contains over 33,000 query paper pairs for training, development, and testing. Although it doesn't show how scientists gather papers, we can still use it for RL training. We also develop a new training method to tackle specific challenges in paper searching, such as sparse rewards and long search paths. To evaluate PaSa, we create a benchmark called Real Scholar Query, which includes real academic queries with relevant papers. Our experiments compare PaSa with several baselines, including Google and ChatGPT. Results show that PaSa 7b significantly outperforms all these systems, achieving notable improvements in recall metrics. In summary, we present PaSa as a comprehensive paper search agent capable of using online tools, reading papers, and navigating citation networks. We also introduce two high-quality datasets for complex academic searches. Despite being trained on synthetic data, PaSa demonstrates impressive performance in real-world scenarios, outperforming existing search tools. Section Summary. In this section, we discuss the challenges of academic paper search and introduce PaSa, a novel search agent that mimics human behavior to enhance literature surveys by autonomously collecting and evaluating relevant papers. We also present two high-quality datasets, Auto-Scholar Query and Real Scholar Query, and demonstrate that PaSa significantly outperforms existing search tools, including Google and GPT-4, in retrieving relevant academic papers. Section: Related work. In this section, we discuss the role of large language models, LLMs, in scientific discovery. We have seen that LLMs can assist at various stages, including brainstorming, experiment design, coding, and writing research papers. A crucial part of research is conducting academic surveys, but existing tools like Google Scholar often fall short, causing researchers to spend too much time on literature reviews. This issue has driven us to create PaSa, an LLM agent that helps researchers autonomously gather relevant papers for complex scholarly questions. We also explore LLM agents, which combine LLMs with memory, tool usage, and planning. This combination allows them to tackle more complex tasks, such as acting as personal assistants, planning travel, performing web operations, developing software, and conducting scientific experiments. Recent research has focused on enhancing these agents through prompt engineering and training. One notable effort is Agile, a reinforcement learning framework that optimizes all agent skills together. We utilize the Agile framework to implement PaSa, specifically designing a new session-level algorithm to handle the unique challenges of paper searching, such as sparse rewards and lengthy processes. To test PaSa in realistic situations, we created Real Scholar Query, a dataset with 50 actual research queries. After launching PaSa's demo, we invited AI researchers to use it. We randomly selected a subset of their queries and filtered out overly broad topics. We then gathered relevant papers manually and used various methods, including PaSa, Google Scholar, and ChatGPT, to find additional papers. We compiled these results into a pool of candidate papers, which were reviewed by professional annotators to select those that met the specific query requirements. The queries in Real Scholar Query were dated October 1, 2024, and examples can be found in the appendix. Professors from a leading Chinese university conducted the annotations, reviewing an average of 76 candidate papers per query. Due to the high cost of this process, we only completed it for 50 instances. Our PaSa system consists of two LLM agents, the crawler and the selector. The crawler interprets the user's query, generates multiple search queries, and retrieves relevant papers, which it adds to a queue. It also processes each paper to identify key citations and adds any newly relevant papers to the list. The selector then reviews each paper to determine if it meets the user's requirements. Essentially, the crawler focuses on maximizing the number of relevant papers, while the selector aims for precision in identifying those that truly fit the user's needs. In terms of functionality, the crawler operates as a token-level decision-making process. Its action space corresponds to the LLM's vocabulary, with each token representing a potential action. The crawler state is defined by the current context and the paper queue. It has three main functions: searching for papers, expanding on citations, and stopping to reset its context. The training of the crawler occurs in two stages. First, we generate trajectories from a small training subset and perform imitation learning, followed by reinforcement learning. Further details on the training process can be found in the appendix. Section Summary. In this section, we discuss the development of PaSa, an LLM agent designed to assist researchers in literature reviews by autonomously collecting relevant research papers. We also outline the architecture of PaSa, which includes a crawler for maximizing paper recall and a selector for ensuring precision, and describe our evaluation method using the Real Scholar Query dataset to assess its effectiveness. Section RL Training. In this section, we discuss the challenges we face when training the crawler using reinforcement learning, RL, particularly the long time it takes to sample a complete trajectory for a query. Each action we take, whether it's a search or an expansion, adds many papers to our list, leading to hundreds or even thousands of papers in the final queue. To tackle this, we define a session as a sub-trajectory that starts with an initial state and ends with a stop action. We recognize two types of initial states, one that includes just a query and another that includes both a query and a paper. We model the crawler as a policy that determines actions based on the current state. We break down the entire trajectory into a series of sessions. Each session consists of a sequence of states and actions, starting with an initial state that can be one of our two types and ending with a stop action. Sampling these sub-trajectories is more efficient computationally. During the training with proximal policy optimization, PPO, we estimate the return for each session using Monte Carlo sampling. We use two discount factors, one for the current session and another for across sessions. After taking an action, we update our paper queue with newly found papers, and we need to factor in the rewards for these papers in our return estimates. To prevent over-optimization, we also include a penalty term based on the difference between our learned policy and the initial policy from imitation learning, scaled by a coefficient. Next, we introduce the selector, which is a large language model, LLM, agent that takes a scholar query and a research paper as inputs. It produces a decision token indicating whether the paper meets the query and a rationale that supports this decision. This rationale helps improve decision accuracy and builds user trust by explaining the reasoning behind the decision. We present the decision token before the rationale to enhance training efficiency for the crawler, allowing the selector to function as a reward model during training. We find that the order of these outputs does not impact performance. We sequentially train the selector and crawler, both based on the Quen 2.5-7b model, to create our final agent, PaSa 7b. The selector undergoes fine-tuning using a specific training dataset, with supervised training for one epoch at a learning rate of 1E5 and a batch size of 4, utilizing 8 NVIDIA H100 GPS. For the crawler, we follow a two-stage training process. Initially, we perform imitation learning on nearly 13,000 training data points, again with a learning rate of 1E5 and a batch size of 4 per device. In the second stage, we apply PPO training, starting with freezing the policy model to train the value model, and then co-training both models. We encounter 5,000 queries during imitation learning and process a total of 16,000 queries during the RL training phase. Further details on data construction and training can be found in the appendix. Section Summary. In this section, we address the challenge of efficiently training the crawler using reinforcement learning, RL, by defining sessions as sub-trajectories that streamline the sampling process. We also describe the selector, an LLM agent that evaluates research papers against queries, generating decision tokens and rationales to enhance accuracy and user trust, while detailing our training methodology for both the selector and crawler. Section: Implementation of search. In this section, we describe our implementation of the search function. This function uses a large language model, LLM, to predict a query based on the context and then searches Google with specific parameters, limiting results to archive.org and a certain publication date. For paper management, we created a database to organize and retrieve research papers. Our system, PaSa, pulls paper information from this database. If it doesn't find a match, we use AR5IV to get the full paper content, including citations, which we then parse and store in our database. We evaluate our paper search agent using two test sets, AutoScholar Query and RealScholar Query. We compare PaSa 7b against several baselines. 1. Google, where we search the query directly with the same settings. 2. Google Scholar, where we submit queries directly to Google Scholar. 3. Google with GPT-4o, where we first paraphrase the query using GPT-4o before searching on Google. 4. ChatGPT, where we use ChatGPT powered by search-enabled GPT-4o, evaluating only 100 random instances due to manual query submission. 5. GPT-o1, where we prompt GPT-o1 to process the query. 6. PaSa GPT-4o, where we prompt GPT-4o within the PaSa framework, allowing for multiple searches and citation network crawling. We designed specific prompts for all baselines, which are detailed in the appendix. The crawling process of PaSa can be visualized as a paper tree. To manage computational costs, we limit the crawler's exploration depth to 3 for both PaSa 7b and PaSa GPT-4o. For Google-based baselines, we measure recall using metrics for the top 20, 50, and 100 search results. For other baselines, we assess both precision and recall for the retrieved papers, comparing the crawler's recall between PaSa GPT-4o and PaSa 7b. Our main results show that PaSa 7b outperforms all baselines on the AutoScholar query test set. Specifically, it shows a 9.64% improvement in recall compared to the strongest baseline, PaSa GPT-4o, while maintaining similar precision. The recall of the crawler in PaSa 7b is also 3.66% higher than in PaSa GPT-4o. When compared to the best Google-based baseline, Google with GPT-4o, PaSa 7b achieves significant improvements in recall across all metrics. We found that using multiple crawler ensembles during inference enhances performance. Running the crawler twice increased recall by 3.34% on AutoScholar Query, leading to an overall recall improvement of 1.51%, with precision remaining stable. To assess PaSa in a more realistic context, we evaluated its performance on RealScholar Query, where PaSa 7b showed a notable advantage, achieving improvements in both recall and precision compared to PaSa GPT-4o. Against the best Google-based baseline on RealScholar Query, PaSa 7b outperformed Google significantly in recall metrics. Additionally, The PaSa 7B ensemble further boosted crawler recall, contributing to an overall improvement in the system's recall. The performance of the selector, which acts as both the final decision maker and an auxiliary reward model in reinforcement learning training for the crawler, is crucial. We collected a dataset of 200 query paper pairs to evaluate the selector's effectiveness. Our results show that the selector achieves an F1 score of 85%, outperforming both GPT-4o and QWEN 2.5 to 7b. Its precision reaches 95%, confirming its effectiveness as an auxiliary reward model for the crawler's reinforcement learning training. Section Summary. In this section, we describe the implementation of our paper search agent, PaSa, which utilizes a large language model, LLM, to predict queries and manage research papers through a dedicated database. Our evaluations show that PaSa 7b significantly outperforms various baselines, including Google and GPT-4o, in recall metrics, particularly in real-world academic search scenarios, while our selector model demonstrates high precision and effectiveness in guiding the crawler's decision-making process. Section: Ablation Study. In this section, we conduct ablation studies to assess the individual impacts of exploring citation networks, reinforcement learning, RL, training, and using the selector as the reward model. Our findings show that omitting the expand action from the crawler significantly reduces recall, with a drop of about 22.98% on AutoScholar query and 32.21% on RealScholar query. Additionally, we observe that RL training improves recall by 6.24% on AutoScholar query and 19.96% on RealScholar query. The RL training curves illustrate a consistent increase in returns as training progresses, stabilizing after 200 steps. Moreover, excluding the selector as an auxiliary reward model leads to a recall decrease of 3.76% on AutoScholar query and 9.63% on RealScholar query. We also explore how to manage agent behavior by modifying the rewards in RL training. We perform experiments with different reward coefficients and present the results. We focus on two metrics: crawler recall and crawler action, where crawler action represents the total number of search and expand actions taken by the crawler. As we increase the rewards, both crawler recall and crawler action rise, indicating that adjusting rewards in RL training can effectively shape PaSa's behavior.